Okay, we're back, and we're now going to do an example over here, and that example is going to be a Cournot duopoly. And actually, could be an oligopoly, could be with more than two firms. So the first thing we want to do is, in fact, basically what I'm going to do here, I'm not going to look at the equilibrium in a Cournot duopoly, although I'll mention it once or twice at the end because it's kind of useful and interesting. But I'm going to focus in the Cournot duopoly problem on one firm's, either of the firms. I'm going to focus on one firm's profit maximizing decision in the duopoly or oligopoly situation. So that means that our firm is going to be maximizing its profit, and its profit is going to be a function of the quantity that it produces and brings to market and the quantity that its rival or its rivals bring to market. And so I'm going to use this notation because it'll turn out that that's instructive. That notation will square, to some extent, with the typical notation that's used when we apply the implicit function theorem in economics. So the firm wants to maximize profit, and let's just point out here that Q is the firm's own production level, and the theta is the rival's production. And let me even point out that so long as the product is homogeneous, it's the same for all the firms that produce it, indistinguishable by the consumers, this could just as well be an oligopoly with multiple firms, and this could be the sum of all the rivals. And so I put the apostrophe out here because in that case I'd have multiple rivals, and this theta in that case would be the total of all the production that's brought to market by all the other firms. So if there's only one other firm, that's the other firm's production. And so what I want to do here is point out that as I go through this example, the Q and the theta are going to be playing the roles of the X and the Y. The pi, that's not going to show up over here yet. So we're going to see something related to the pi, but the pi isn't playing the role of anything over here. But the Q will be playing the role, the Q. Now, let's back up just a little bit and try to see why the Q and the theta might be playing the role of the X and the Y, or the Y and the X. So we're looking at this from the point of view of the particular firm that's maximizing its profit by choosing its production level. And that is presumably for that firm going to be a function of, or it's going to be determined by what the other firms are doing. So it looks at what the other firms are doing and reacts to that. And in fact, what we're developing is the firm's reaction function. And so if the Q is the firm's reaction to theta, then it's the theta that's the independent variable in the firm's problem, exogenous to the firm. So the theta is playing the role of the X over here. So let's write that the theta is playing the role of X, and the Q is going to be a function of what the other firms are doing. If the other firms produce more, then our firm will probably produce, let's say, less, perhaps. If the other firms produce less, our firm will produce more. So the Q would be a function of theta, just like the Y is a function of X. So the Q would be playing the role of the Y over here. We haven't got anything yet playing the role of capital F or C or anything. So we have our profit function. I won't write out a particular profit function here, but let's look at the first order condition. The first order condition for our firm maximizing its profit is, of course, that the derivative of its profit with respect to its choice, its quantity, that derivative, of course, is a function of Q and theta. It's going to depend on both the firm's own production level and the other firm's production level. That's got to be 0 as a first order condition. And we're going to ignore second order condition here. But this is the first order condition. This is 0 so long as we're in the interior, so long as Q is positive, not at 0, in which case that'd be an inequality then. And of course, this is the same as saying the marginal revenue equals the marginal cost. The derivative of the profit function is the marginal revenue minus the marginal cost. Marginal revenue depends on Q and theta. Marginal cost depends only on the firm's own output, and those have got to be equal. That's the first order condition, but I'm going to, of course, write this as marginal revenue minus marginal cost equals 0. So two different ways of writing the same thing here. And so let's define function. In fact, let's look at the linear case. Let's look at the case of linear demand and linear cost. So let's write that here. If demand and the firm's cost function, demand and cost are linear, then demand and cost are linear, then the profit function, in fact, the revenue function, will be quadratic. If demand is linear, the revenue function will be quadratic, and its derivative, the marginal revenue, will again be linear. And if the cost function is linear, then that's linear. So if demand and cost are linear, pi is quadratic, but the first order condition expression, the derivative of profit, is again linear. And since it's linear, let's write it as, in fact, let's write it down here. I'll again write Q and theta to emphasize these depend on Q and theta. This is going to be a linear function. It's going to be some number alpha minus, let's say, some number A times Q minus some number B times theta. I have that reversed from what I want. I mean, I could write it that way, but it won't square with what I have over here. So let's reverse that. So minus let's say A times theta minus B times Q minus some number, let's say beta. Okay, and that's got to be 0 as our first order condition. So I've rewritten the first order condition as a linear function, and in particular, this is what it will look like. It will look just like this, and in fact, this will be the derivative of the cost function. It will be the marginal cost. And the rest of this will be the marginal revenue, which indeed, as it says here, is a function of both Q and theta. Marginal revenue is downward sloping with respect to the Q, as we're used to seeing it. So marginal revenue minus marginal cost is 0. This linear expression has to be 0. And so I'm going to rewrite this so that it looks like what we have over here. I'm going to rewrite this as I'm going to define a function f of Q and theta, and that's going to be A theta plus BQ minus C equals 0, where C is alpha minus beta. Okay, so let's just make sure that I did the arithmetic right here when transforming this expression here on the left. So what I've done is I've said I'm going to pull these two terms over to the right. That's A times theta plus B times Q. And then I'm going to say that has to be equal to alpha minus beta, which I'm going to call C, and then I've pulled that over here too. So this is the same as this over here, and in fact, let's even write this here, and let's take this off, so it looks even more like what's over here. Okay, this is now f of q theta. Let's let that be f of q theta. Looks just like this. Theta is playing the role of x. Q is playing the role of y. And so the implicit function theorem for two real variables, linear equation holds. And so what we have is 1, and let's even put this in pink again, square with what we have down here. We have the y variable here, which is the dependent variable, which is q. We have q equals f of theta equals c over b minus a over b times theta. That is our explicit function, which comes implicit, comes from this expression here implicitly. And let's write the derivative here. That is going to be f prime of theta, and that's obviously minus a over b. And all of this, of course, is true if b is not 0. Well, would b typically not be 0 in this situation? Actually, let me point out, maybe I'll write this in yet a different color here. In this context, it actually turns out that b will, so long as the product is homogeneous, the same product as being produced by all the firms and the consumers can't tell the difference, then the b will be actually equal to 2a. So let's just point out down here that b equals 2a in this duopoly situation. And when you work this out in, if you've worked it out previously in your undergraduate program, or you'll work this out in your first equilibrium or imperfect competition course in the first year of your program, you'll find that indeed the b will be equal to 2a, and what that means is that this is going to be minus 1/2. Let's look at one. Let's look at this function here. Let's draw the picture. So the picture here, the diagram, is going to look like this. Let's say this is theta. This is q. Again, theta is our rival firms, or the total production of all the rival firms, if we have more than one rival. Q is our own production, and this is going to be a straight line. It's going to be c over b minus a over b times theta, and the slope will actually be minus 1/2 in, so long as we have b equals 2a. If the good's not homogeneous, then things are a little more complicated, and b won't necessarily be equal to 2a, but if we still have linear demand and cost, everything will still be linear. So this is, it's exact, in fact, well, let's write it here. Q equals f of theta, and of course, it's this linear expression here, and this is what we call the firm's reaction function. This is the firm's reaction function, telling how it reacts in its production decision to the production decision of its rival or rivals. And this is the firm's reaction curve, which is just the graph of the reaction function. Let's see, I think there's one or two other things that I wanted to point out here. Yes, and that is, let me even write this in a different color here. That is that the function here is, of course, just the solution function, which we've talked about before. We had a whole lecture, in fact, on the solution function and the value function. And you'll recall there that we said that to find out about how the solution function works, if the solution function is well defined, what its derivative will be, we said then that the way we'll address that will be with the implicit function theorem. And then we said we would use, I believe, the envelope theorem to be able to analyze the value function. That's something we'll do next, not today. And this is, of course, also called the firm's decision function because it tells, whoops, let's try to spell that correctly. It's getting worse, not better. The firm's decision function, telling us the firm's decision as a function of the environment that it finds itself in particular, as a function of what its rival firm or firms are doing. And let's also point out that this is a classic economics application of the implicit function theorem. Application to an optimization problem, and in particular, an application to the first order conditions in the optimization problem. And that's a classic application exactly because what we're working with is the solution function for an optimization problem. And so that's one of the ubiquitous in economics applications of the implicit function theorem is to optimization. I'm going to get down a little lower here so I can write this a little better. And there is a second ubiquitous in economics application of the implicit function theorem, and that's to equilibrium analysis. And for that, let me mention just a couple of things quickly. The function that, and let's focus on the function here. And in fact, for doing this, let's even make the right-hand side the c. Let's make it a 0, okay? And so in equilibrium analysis, this function is the excess demand function. And so to have the excess demand be 0, that's typically our equilibrium condition, and that just means demand equals supply. So demand equals supply means demand minus supply, excess demand is 0. Just like over here, the derivative of the profit being 0 said the marginal revenue equals marginal cost. Marginal revenue minus marginal cost is 0. Demand equals supply, demand minus supply is 0. And in that kind of analysis, the x and the y, the x might be the prices that come out endogenously. The y would be the prices that come out endogenously, and the x, the parameters, might be tastes, might be the weather, might be production conditions, costs of production, availability of inputs, and so on, would be the parameters. And the implicit function theorem helps us say when we actually do get the equilibrium prices, let's say, in our application, equilibrium prices as a function of the parameters. I should be pointing here for prices, here for the parameters, so that y does come out as a function of x, prices as a function of parameters, and we get the derivatives of how the prices change as parameters change. These are the parameters, the y's are the prices. The derivatives here tell us how prices change in response to changes in the parameters. And so these are the two applications of the implicit function theorem that you will see repeatedly over and over again in certainly in the first year of your program, and in fact throughout the program, throughout your career as an economist, you're going to see the implicit function theorem applied to these situations. Okay, so what we want to do now is we want to take some of this off, probably take all of this off, and we're going to come back and we're going to look at the situation when we have a nonlinear function. And of course, notice that I haven't actually stated the implicit function theorem explicitly as a theorem yet. So we're going to come back and we're going to look at the situation when f is not linear necessarily. And then we're going to actually write down the implicit function theorem, and then we'll go beyond that to look at the situation where the x's and the y's are multivariate, multiple variables, and we have multiple equations. And we'll look at the implicit function theorem in this much more general case, and we'll probably come back and do one more application. So that's where we're going to go next after we take all this off. Whoa, it turns out that we're not going to take everything off quite yet, because there were a couple of things that I want to say about this linear case here before we take the linear case off and go to the nonlinear, more general situation. First, let me say that, of course, we don't really need the implicit function theorem for this linear case, either for the Cournot duopoly. We don't really need the implicit function theorem to do what we do over here in the linear case, linear demand. So we have linear first order condition. And in fact, I actually teach the Cournot duopoly, the linear case, when I teach intermediate microeconomics at the undergraduate level. It's simple. Of course, I don't use the implicit function theorem there. So we don't need the implicit function theorem there. And we don't need the implicit function theorem more generally over here. We can, of course, easily get the function y equals f of x, where the function is c over b minus a over b times x. And this works if and only if b is not 0. We don't need the implicit function theorem to do any of that. And so the reason that I started with this simple linear case is, as usual, it's a situation that is completely familiar, simple, almost trivial, but by using that as the starting point for the new concept that we're really interested in, that new concept is completely transparent in the familiar, simple, in this case, the linear example, the linear case. And so that's a good place to start. And then, of course, we're going to move on to the not so transparent, not so simple, nonlinear case. But everything we did in the linear case kind of carries over in terms of the intuition, intuitively. Okay? Now, the second thing that I want to say about this linear case is that with a linear function, capital F, the partial derivatives, capital F sub x, capital F sub y, don't depend on where we're evaluating those partial derivatives. F sub x is just a, and it's a no matter where we are. F sub y is b, and it's b no matter where we are. So the partial derivatives don't depend on the point xy in the space where we're working. And of course, therefore, the derivative of little f, f prime of x, is the same everywhere as well. It doesn't depend on x, doesn't depend on y. And so that will carry over to the linear case when we have lots of variables, lots of x variables and lots of y variables. It'll still be the case that again, we won't need the implicit function theorem because we can do everything there with matrix algebra. And everything that we did here was true kind of globally across all the x, y points. And even when we go to the multivariate case, a linear function, if everything's linear, then we won't really need the implicit function theorem. Everything that we do will be true globally because the derivatives don't depend anywhere on x and y. They're the same everywhere. And so that's going to turn out to be important in just a few moments when we do go to the nonlinear case. So that kind of summarizes, I think, everything that we need to know about the linear situation, the linear case of the implicit function theorem, at least in the two-variable xy kind of case. And so now we will take all of this off, and when we get everything off, we'll be back and we'll start on the nonlinear case. Okay.